Yeah, apologies for the delay. Welcome to the session on MPC and FSS. We have three talks. The first talk is titled Compute but Verify Efficient Multi-Party Computation over Authenticated Inputs. And Momita will be giving the talk.
Thank you for the introduction. I'm Momita Atta, currently pursuing my PhD under the guidance of Dr. Chaya Ganesh and Dr. Arpita Patra. And today I'll be presenting our work, which is a joint work with my advisor Chaya Ganesh and collaborators and mentors Shikha Patra Nabis and Nitin Singh. Let's get started. In multi-party computation enables multiple parties to come together to compute a joint function on their private inputs. The key goals of providing a secure multi-party computation is to ensure that at the end of the computation, the output is correct while ensuring that the input of privacy of the input is guaranteed. That is, that nothing about the input is revealed beyond what can already be inferred from the output. Traditionally, MPC handles corruptions like parties may be semi-honest, where they follow the protocol specification but wishes to learn more from the protocol execution, or parties may be malicious, where they arbitrarily deviate from the protocol. Traditional MPC guarantees do not cover the scenario where the inputs might be corrupted. For example, let us consider the 2PC AND computation, where if we supply the input 1 every time, we can always learn the other party's input. But this is not a breach of privacy. So these kind of data poisoning attacks are not handled traditionally and might be relevant to applications like secure aggregation in ML. A solution that we propose is we can authenticate the inputs that are used inside MPC. So our goal is to ensure that authenticated inputs are used inside MPC, and a key performance requirement to do the same is to ensure that we incur negligible communication and computational overhead on top of the existing MPC. We should be able to support it with existing infrastructure. Now, to achieve authentication, first we need to define what are authentic inputs. We say that any input that is signed by certifying authority is authentic, and the next obvious question is to ensure that those inputs are used. So we do that by input verification. Verification of the signature is consistent with the used input. So it boils down to the two steps: getting an authentic input from the certifying authority and then determining that the input used is indeed consistent. Now, first we can attempt to authenticate inside MPC, that is, do the signature verification inside MPC. But recall that MPC works with addition and multiplication gates, and signature verification might involve algebraic relations, which we would need to represent as in an arithmetic circuit, which would be very expensive. So what we propose is to authenticate the inputs outside in MPC instead, and the key challenge to do that is to link the signed message with the input that we are using inside MPC. I'll briefly summarize our contributions here. We provide an efficient compiler that transforms any secret sharing based honest majority MPC into one which also has input authentication ingrained in it. As a building block, we use robust distributed proof of knowledge for algebraic signature schemes. These are of independent interest as a primitive. And as a performance guarantee, we provide communication overhead of order of n squared log L to authenticate L size input for all of the n parties involved in the MPC. We first look at our first contribution of distributed proof of knowledge as a primitive. Here, the witness is distributed to the parties, and parties collectively wishes to prove something about the distributed witness. So here, at least our relation of interest is of discrete log in our work. So we wish to prove something about the witness W, where the witness W is distributed amongst multiple parties. In this, we provide a robust distributed proof of knowledge, which can provide security even in presence of dishonest usage of shares. Then we provide a construction of DPOC for the discrete log relation. Using that, we also provide this DPOC for algebraic signature schemes like BBS plus and PS. And finally, we provide an efficient, round efficient version of the same in the random oracle model. Using our distributed proof of knowledge as a building block, we provide our compiler, which will take as input any secret sharing based honest majority MPC and output an MPC with authenticated inputs. This will incur less computational and communication overhead on top of the input MPC. There are several works that handles input authentication. There are works by Baum, Katz et al., Zhang et al. That does input validation for 2PC. There are recent works by Blanton and Zhang that constructs MPC for a specified class of MPC that has input authentication ingrained in it. And there are work of Arana et al. That provides signature verification with respect to PS signature schemes. Now, both the works of BJ18 and ADO21 works as follows. It will generate authenticated secret shares, and then you're supposed to use those authenticated secret shares in the MPC to get authenticated inputs. Now, note that this framework would require us to have additional checks to ensure that the same authenticated secret shares are being used inside the MPC itself, right? For that, we use our debug as a primitive. And before looking into that, let us look at why we need to introduce the notion of distributed proof of knowledge. So first, let us take a step back and look at classical proofs, where a prover wishes to prove something about the secret witness it holds, and it wishes to prove that it knows a witness with respect to a public statement. For that, it interacts with the verifier, at the end of which verifier outputs whether it's convinced or not. We have several guarantees from the classical proofs, like that of completeness, where we ensure that an honest prover is always able to convince the verifier. We have the guarantees of soundness, where we ensure that a malicious prover does not convince the verifier with an overwhelming probability. And we also have the guarantees of zero knowledge, where we ensure that a malicious verifier learns nothing extra from the transcript, from the interaction with the prover. Now, recall that we are trying to use these proofs to prove input authentication of inputs inside MPC. Now, this would require each of the parties to prove that its input is authentic to all of the other parties involved inside the MPC. So if we try to plug it in naively in MPC, we would require order of n square proofs, and that is not very efficient, is it? So instead, we work with distributed proofs of knowledge, where we work with the following. The prover secret shares it with its witness to a bunch of workers, and then the workers will then interact with the verifier to convince the verifier of the claim with respect to the witness that is held by the prover. I'm sorry, the animations are off, so I am just showing the complete slide right away. So like we had in classical proofs, we also have, the guarantees we have in classical proofs, we also have the guarantee of soundness in distributed proofs, where we ensure that if a prover is malicious, it is not able to convince the verifier. That is, if a prover generates the shares with respect to a malicious witness, then when the workers use the malicious shares to interact with the verifier is not convinced. And similarly, we also want to ensure that an honest prover is able to convince the verifier even if some worker in the middle decides to participate with some dishonest share. Now, we'll briefly look at our overview of the compiler. So our compiler will take as input a secret sharing based MPC and split it into two parts. First, it will run the secret sharing phase, and then it will run the online phase. Once we have split it into two parts, it will output the next MPC, which has input authentication, as follows. It will run the secret sharing phase, and before running the original online phase, it will run the input authentication phase using our distributed proof of knowledge for the specific signature schemes, algebraically structured signature schemes like BBS plus and PS. Now, the nice thing about the proof of knowledge of these two signature schemes is that both proof of knowledge of PS signatures and BBS plus signatures reduces to proof of knowledge for discrete log relation, which looks like this, that you know discrete log with respect to two publicly known elements. The outline of the rest of the talk is as follows. We first look at robust epoch for discrete log relation. Then we look at robust epoch for the signature schemes. And then we look at an overview of our compiler. For that, we first look at proof of knowledge for discrete log relation. We see how to distribute it, and then we see how to ingrain robustness into it. So recall that proof of knowledge of distributed discrete log relation looks like this, where we have a 3-move protocol. The prover samples a random element and sends the commitment to the random element across. Verifier samples a random challenge. It sends it to the prover, and then prover responds with a linear combination of with respect to the verifier's challenge and the random element it had sampled, and sends the response to the verifier. The verifier finally checks that the relation holds. Now this turns out nicely if the prover is honest, and we are not going to discuss the soundness guarantees in this presentation for now. So note that if we wish to distribute this sigma protocol, first the prover needs to generate secret shares, and then it shares them with the workers, and we will work with additive secret sharing for starters. So here, let us look at the top half, where the prover has generated the secret shares, send it to the verifier, and the verifier has the shares with it and the public elements with it. Now, worker will do exactly what the prover was doing in the previous round, and it will send a commitment to the random element, get a challenge from the verifier, and send a random linear combination with respect to the challenge sent by the verifier. It works out nicely because it is in the broadcast model, and the challenge sent by the verifier is uniform across all the executions done by the worker. Now note that this would fail even if one worker is corrupt, and this is what we wish to avoid. So what we wish to provide is that honest input should be authenticated even if some shares are used maliciously. To do that, we use the concept of error correction. For that, we use a linear secret sharing scheme, and we leverage these properties that linear combination of code words is also a code word, and if you take a linear combination, then the error of the position of the error is also retained. To be precise, let us look at this, where we have shares of inputs A, B, and C across all the parties P1 to Pn. Now, if party P2 is corrupt and it uses some random malicious shares with respect to the inputs A, B, and C, then if we take the linear combination will also preserve the error location, and if we error correct with respect to the last line, we would be able to identify that the error was in that position, and we would be able to error correct. Now, when we try to provide the distributed proof of knowledge, the prover additionally needs to sample a random element and also send it across to all the workers as an auxiliary input. And then we work with the broadcast model again. The worker will send commitments to its shares across to the verifier, and verifier responds with a random challenge. Now note that here it is exactly doing what the party P2 was doing in the prior slide. It is taking a linear combination with respect to the challenge sent by the verifier with its own the shares held by the worker. And finally, both the worker and the verifier runs a proof of knowledge to ensure that those commitments can be used and are consistent with the values that are used by the worker. And finally, the verifier will run error correction, and because of the guarantees we saw before, we can ensure that this will retain the position of error. And finally, we do error correction and get back the original value and check if the original value has been used correctly. Now let us look at PS signatures quickly. For that, we first need to look at the syntax of bilinear groups. Bilinear groups is represented by what we see above. It is represented by a prime element Q, G1, G2, and GT that are groups of order Q. Small g and small h are generators of the first and second group, and E is a bilinear map which takes element from G1 cross G2 to GT. And what nice property is admitted by the bilinear map is that it is somewhat irrelevant where the exponent is, if it is in the first group, second group, or the target group. So the PS signature looks like this, where the keygen algorithm samples the secret key at random. It samples a bunch of random elements and sets the public key as follows by taking the generator of the second group and raising it to the secret key. The sign algorithm then generates the signature by sampling an element, non-zero element from the first group and taking the second element as raising it to some linear combination of the secret key. Finally, the verify algorithm will check if the first element is indeed non-zero and second element has the similar structure as is shown by the sign algorithm. Now note that these two relations, the first relation is a discrete log relation in the group 1 and the second relation expands to a discrete log relation in the target group. This is what is used by the proof of knowledge of PS signatures. It will re-randomize the signature so that we can not link the two executions of usage of signature. But the key point is here that proof of knowledge of opening for PS signature reduces to proof of knowledge for discrete log in the target group. So to provide robust distributed proof of knowledge, we can have the workers and the verifier run a robust distributed proof of knowledge with respect to the target group elements. Similar to PS signatures, proof of knowledge for BBS plus signatures also reduces to discrete proof of knowledge for discrete log. So we can use similar techniques to extend it to BBS signature as well. Now we look at a brief overview of our compiler. Our compiler looks as follows. Compiler will first run the secret sharing phase of the input MPC. Then before running the original online phase of the input MPC, it will run an input authentication phase. In input authentication phase, the goal is to authenticate inputs of all the parties involved. So let us say that we are trying to authenticate PI's input XI, then all parties PK will work as a worker to generate the proof, and all the other parties will also act as a verifier. We take an example to look at this. So let's say we are trying to authenticate P3's input X3. So P1, P2, P3, and P4 will already have shares of X3 from the original secret sharing phase. It will work as workers to generate the proof for P3, and then it will also act as verifier to be convinced that the P3's input was indeed correct. And finally, we run the original online phase. Now note that this input phase takes less computational and communication overhead on top of the underlying unauthenticated MPC execution, and this is a key performance requirement in our work. So note that to run the original MPC, if we require 125 seconds, then the time required for running our debug instance is just 6.2 seconds. And if the communication overhead is in MB for running the MPC, then we require only KB's worth of communication for running our debug. To conclude, we provide a robust distributed proof of knowledge that works for multiple provers. Then we provide a construction for the same for algebraic signature schemes like BBS plus and PS using distributed proof of knowledge for discrete log relation. And finally, we provide a compiler that takes as input an honest majority secret sharing based MPC and outputs an honest majority secret sharing based MPC which has input authentication ingrained in it. And this preserves the security guarantees of the underlying MPC as well. Thank you. I would be happy to take questions.
We are behind schedule, but if there is a very quick question, we can accommodate one while the next speaker sets up.
Hello. How does the protocol handles adaptive adversaries?
We are working with static adversaries as of yet.
Okay.
Yes. So, and mostly it is in dishonest honest majority settings. So that is also.
Okay, let's thank Momita again and move on to the next talk.
Thanks.
The next talk is on the concrete security of two-party computation, simple definitions and tight proofs for PSI and OPRFs. The speaker is Rishabh Ranjan.
All right. Hope everyone can hear me clearly. Hi, hello everyone. The work I'm going to talk about today is brings new directions to two-party computation, namely concrete security, and the simple new definitions that enable it. The applications of our framework are to the private set intersection and oblivious pseudo-random functions functionality. This is a joint work with Mihir Bilare, Doreen Reaper, and Ali Aldakil, and my name is Rishabh Ranjan. So everyone here probably already knows about two-party computation, but to ground our discussion, I'll like to identify some of its key elements. Uh, in two-party computation, we have two parties, party 1 and 2, where uh, they take party 1 and 2, where they engage in an interaction and try to get some outputs. The functionality F here defines how these outputs will be created. As an example, we have the private set intersection functionality here. The inputs are sets. The first party intuitively gets the intersection of those inputs, and the second party gets nothing. Formally, however, we also add that the set sizes are revealed. So here, as we can see, fx1 and x2 1 is the output for the first party, and fx1 x2 2 is the output for the second party. A protocol pi for a functionality defines the steps that the parties have to follow to compute their messages so that they can get the desired output. A protocol can be secure or not. Security is defined. The security goal is that for any party, they should not be able to learn about the inputs of the other party except what they can already learn from the outputs that they receive. So the first wave of two-party computation research started with Andrew Yao and was theoretical, asking whether this magical sounding goal can even be achieved. The significant contribution of this work was to show that secure protocols exist and for all, that is, arbitrary functionalities. And at that time, efficiency was not much of a consideration. It was enough that the protocols were polynomial time. Security was shown in the usual asymptotic framework and asking that the advantage of polynomial time adversaries be a negligible function of the security parameter. We are now in the second wave. There is an increasing practical interest for two-party computation functionalities with applications and implementations. This wave is fueled by research aiming for protocols as efficient as possible. And they are not necessarily for generic functionalities, but they try to focus on particular functionalities like private set intersection or oblivious pseudo-random functions. And as with other areas of cryptography, designs often use the random oracle model and prove security under particular computational assumptions. However, this practical side of two-party computation is incomplete in an important way. Namely that the setting for security proofs remains asymptotic than the concrete security one. And this is in contrast to other areas of cryptography where concrete security proofs are mostly used for applied work. So this is a major gap because without a concrete security treatment, implementers do not have a proof justified way to pick parameters such as like size of elliptic curves. And so they are not able to guarantee a desired level of security. One may, for example, have two protocols and both asymptotically secure, but on a 256-bit curve, one provides 128 bits of security and the other only provides 64 bits of security. So in an asymptotic security proof setting, these kinds of results are hidden. So this is the gap that our work fills. And so we provide a concrete security treatment of two-party computation. The outcome is that we have results which allow one to pick parameters that guarantee a desired level of security. And for example, if somebody desires 128 bits. So let me briefly summarize our contributions. So in this work, we initiate the study of concrete security for two-party computation. Our first results are definitional. We presented an indistinguishability-based definition called input indistinguishability, abbreviated as INI, which provides the same level of security one would expect from simulation-based definitions for a class of functionalities that includes private set intersection and its variants. These, as I've noted, many current proofs of two-party protocols use the random oracle model, but it is often not explicit in their definitions. Our formalizations fill this gap too. So we explicitly incorporate the random oracle model, and our detailed treatment surface some subtleties regarding random oracle model programming in these definitions. So using these definitions, we apply these to a very canonical protocol called DHPSI and get concrete security results. We do this in two steps. First, tightly reducing the security of DHPSI to 2HDH of BRF, which was given by Jarecki and others, and then reduce the security of 2HDH of BRF to several different assumptions, Diffie-Hellman-based assumptions. And as we can see in the picture, some of them are tight, some of them are non-tight, based on the assumptions that is used. Next, we also give a new PSI protocol called salted DHPSI, which provides tighter security than the DHPSI protocol, but while being as efficient as the DHPSI protocol. I would like to note that all of our results are in the semi-honest setting and are for deterministic functionalities. And extending these to the malicious setting or for randomized functionalities is important future work. So some remarks to put our work in context and see implications. The concrete security treatment of cryptographic principles started or cryptographic schemes started with the work of Bellare and Rockaway in the 1990s. It has since become the norm for security proofs in some areas like symmetric cryptography, applied public key cryptography, and authenticated key exchange. There is a huge amount of literature in this, which follows up on this work. And proof tightness is a popular theme among this research. So, however, in two-party computation, this has not been the case yet, barring some of the concrete security treatment of garbling circuit-based schemes. So this is the gap we fill, bringing concrete security treatment to two-party computation with new definitions and results. We see this as an opening for new research directions, in particular to give and improve concrete security analysis for existing schemes, give tighter proofs, and allow sound choices of parameters to achieve a desired level of security. So for the rest of the talk, I'll quickly go over some background about asymptotic and concrete security. Then I'll I'll present our definitions and its relations to the existing simulation-based definitions. And then I will give the results for the DHPSI protocol and the new salted DHPSI protocol. So the setting for proving security, whether it is asymptotic or concrete, is that we have a scheme or a protocol pi that we want to show achieves some notion of security, say T, based on some problem P, which is hard or assumed to be hard. In both of these cases, what we do is give a reduction that takes an adversary A, which is attacking the T security of pi, and construct an adversary A prime, which is attacking the problem P. In the asymptotic security setting, the reduction will tell us that if the adversary A runs in polynomial time and has negligible success probability or advantage, then the adversary A prime also runs in polynomial time and has advantage that is not negligible. So time and advantage here are functions of security parameter, and negligible means that the function vanishes faster than the reciprocal of any polynomial as the security parameter goes to infinity. In the concrete security setting, we have that the running time of adversary A is some parameter T, and the advantage of adversary A is epsilon. We assume, as is usually the case, that the constructed adversary A prime has also running time about T. And with that, we give a bound on epsilon, which is an explicit function of epsilon prime, which is the advantage of adversary A prime. And for example, the bound could be 2 times epsilon prime. And here, I'm simplifying a little bit. The bound can also be a function of oracle calls that the adversary makes. So now, if someone asks, how many bits S of security does pi provide if we are working with a 256-bit curve and the underlying problem is discrete log? In the asymptotic security case, we don't get a direct answer. Indeed, the security that it provides could be 0. But in the concrete security case, since we know that discrete log provides 128 bits of security for a 256-bit curve, and the bound is 2 times epsilon, we know that it provides 127 bits of security. So moving on to definitions and relations, it is our thesis that some definitions are more easier to work with for concrete security treatment. So we define a taxonomy that divides security definitions into 2. So we have single quantifier definitions, which asks that for all adversaries, the advantage should be bounded. So this is the kind that we are mostly interested in, including, and we mostly see including common definitions like the indistinguishability-based definitions. And in our prior discussion of concrete and asymptotic security, we also assumed this kind of definition. The second category is double quantifier definitions, and it involves some entity like a simulator. And the simulator is now existentially quantified, and this creates a more complex definition. The presence of the simulator complicates concrete security treatment, and to be clear, they are not impossible, but just hard to come up with. And from this perspective, single quantifier definitions emerge as preferable. And but one must consider that the double quantifier definitions also have some advantage. Mainly, they are traditional and intuitively provide strong security. So a natural question now arises is whether we can have the best of both worlds. And in other areas of cryptography, like encryption, we already know that this is true. For example, in encryption, we have indistinguishability-based definitions and a classical results, which says that these definitions are equivalent to the simulation-based semantic security definitions. We are asking whether can we have something like this for two-party computation? And our work answers this in the affirmative. In particular, we give an indistinguishability-based definition called INI and show that for a class of functionalities, the security that it provides is equivalent to a simulation-based definition called SIM. So now this supports focusing on INI for concrete security. To explain INI, we start with a warm-up. I'll recall the indistinguishability-based definition that is used in encryption. This is given through a game. On the right, we can see a formal description of the game. On the left, we have a pictorial representation for the game. The game first picks a challenge bit and initializes the key K. Any adversary who is playing the game has access to an encryption oracle to which it sends two messages. The encryption oracle computes a ciphertext based on by picking one of the messages based on the challenge bit B, and sends back to the adversary the ciphertext. And the adversary can make multiple calls to this oracle. At the end, adversary makes a guess for the challenge bit and wins the game if it guesses correctly. The advantage for the adversary is defined using this equation, which just means that how much better it performs than just randomly guessing the bit B. We want to give something similar for two-party computation, and the idea that we had can be seen by this analogy. The two messages for encryption will be two inputs for honest party, here set to party 2. The adversary also provides one input for the dishonest party. The role of the ciphertext is played by the view of the dishonest party in an interaction where the honest party has input x_2b. A subtle point here is that a trivial win arises if the dishonest party outputs differ on the challenge inputs. So we disallow this, and in this analogy, it's similar to disallowing different linked messages for the encryption game. Before we look at the INI definition, I would just like to quickly put forward this XT definition that is present for to formalize the execution of a protocol. In here, XT takes as input the inputs for the parties and the coins for the parties, and returns the conversation transcript, which are the messages that the two parties would send each other, and the outputs for the parties. Here we have the input indistinguishability definition, also called INI. Again, the game picks a challenge bit B. The adversary has access to an oracle called run, and it queries this run oracle with a 3-tuple, where the first part of the tuple is just an input for party 1. Here, party 1 is the dishonest party. And the next 2 tuples are 2 inputs for the honest party. The run oracle picks random coins, runs the XT algorithm, and returns the conversation transcript and the output and random coins for the dishonest party to the adversary. Again, the adversary can make multiple calls to this run oracle. And finally, it makes a guess for the challenge bit and wins if the bit is correct, or it guesses the correct challenge bit. The advantage of adversary is similarly defined. So if we leave the definition as it is, there is a trivial win for the adversary, as I previously mentioned. If it queries the run oracle with inputs such that the output that it receives from the 2 pairs of inputs is different, then it can just trivially win. So we solve this by adding this requirement that the output from this is the output from the 2 pair of inputs is the same. Here we have a formalization of our game. I would not go into details for this. I'd just like to point out that we have the random oracle, which which we explicitly incorporate in the game, and the random function is initialized in the game. We also give some simulation-based definitions, namely SIM, which is in the programmable random oracle model, and SIM-NP, which is in the non-programmable random oracle model. The games for these definitions are also parameterized by a simulator. I will again not go into details for this, but I would like to take this time to highlight a subtle point that arose when we were doing a detailed treatment of these simulation-based definitions. So apart from just the adversary and the protocol, the functionality might also access the random oracle. And if we allow the outputs of the random oracle for the functionality to be programmable by the simulator, we can show that some obviously insecure functionalities are secure. And so our definitions do this in a different way, where we have the game also select a honest random function and use that to answer the functionalities query. Some remarks about our definitions. We allow multiple queries to the run oracle, which correlates to multiple executions, and we incorporate ROM explicitly in our model. There are some relations. It would not be good if INI did not provide the same level of security as the simulation-based definitions. So through various claims in our papers, we show that INI implies SIM-NP and thus implies SIM for a class of functionalities which we call invertible. What is this invertibility condition? So here I'll illustrate it with party as 2. And the idea is that there should be an efficient algorithm IA such that given some input and output for the dishonest party, it produces an input for the honest party, under which the output of the dishonest party remains unchanged. In our paper, we also show that the PSI functionality and its variants are invertible, which is easy to see. The variants that we consider are threshold private set intersection and cardinality private set intersection. So to conclude from this definitional framework, since PSI and related functionalities are invertible, we can get the same level of security that is provided by simulation-based definitions by targeting INI definition. And so we can get this concrete security-friendly definition for these functionalities. I'll quickly go through the results for DHPSI for our paper. The DHPSI is a very popular PSI framework, which was given, or PSI protocol, which was given by Jose and Lindell when the underlying OPRF is initialized by the 2-DH OPRF. The way we get to the results for DHPSI is a 2-step process. I won't go into the details, but I'll just show the results. Our results are under various assumptions. The CDH and DDH are the regular computational and decisional Diffie-Hellman assumptions, and we get to the other assumptions by giving more power to the adversary. The setting for our result is, again, similar to what we saw before. Adversary A is attacking the INI security of DHPSI, makes some oracle queries, and has some advantage E. Using this, we build an adversary A prime, which is attacking a problem P and has about the same running time and some advantage. And we get the following bounds for this, for the adversary A. As we can see, CDH does not get very good bounds, but we get better bounds or tighter bounds as we go to the VCDH MUC assumption and the DDH assumption. We also do a concrete secret. We also give a new salted DHPSI protocol, which adds salting to the DHPSI protocol to achieve tighter security. And as we can see, the bounds for salted DHPSI are much better than the DHPSI protocol. In fact, we get tight bounds for VCDH assumption as well. And one thing to notice as well is that the Q-run doesn't appear as a factor in these bounds, which just means that we have tight multi-execution security for salted DHPSI. So with this, we come to the end of our end of this talk. To summarize, we initiate the study for concrete security treatment of two-party computation. For this, we gave a new definition, which is indistinguishability based, but is equivalent to the simulation-based definition. For a class of functionalities, we apply this to DHPSI to get concrete security results and also give a new PSI protocol called salted DHPSI, which has tighter security, but is as efficient as DHPSI. Thank you.
Any quick question for Rishabh? Is there a question there?
So you mentioned that there was ways to go in upgrading this to active security, for example, but I wondered if you see a similar problem in the definitions not really serving the goal of concrete security and more general multi-party computation as well. Is that another thing that you wanted to look at?
Right. So from what I can understand, you're asking whether we can upgrade these definitions to active security and also look into like similar problems in multi-party computation case?
Yeah, I was wondering, sorry, I guess I was wondering if you encounter the same problem if you sort of move your number of parties more than two.
Mm-hmm. Yeah, you would definitely encounter a similar problem. I would, although we haven't looked into this specifically, but I would assume that for some kind of threshold, you may be able to reduce multi-party setting to a two-party setting. But yeah, we'll have to look into that particularly.
It was like the start of quite a lot of works.
Yeah, yeah.
Thanks.
Okay, let's thank Rishabh and move on to the last talk of the session. Unfortunately, it's a remote talk. Direct FSS constructions for branching programs and more from PRGs with encoded output homomorphism. The speaker is Jay Lee.
You see my screen? Hey, Chair, can you see my screen? I shared my. Can you see my screen? Can you see my? Okay. Thank you. Huh? Only. Okay. Okay, now it's okay. So, thanks to the introduction, and I'm Zheli, and I will talk our recent work on function set sharing for branching programs and others for from PRG with EOH. This joint work was with Elliot, Lisa, and Peter. My talk consists of three parts. The first part is a brief introduction on the function set sharing, and the second part is on our results, and then I will give the techniques to implement our results. For function set sharing is a secret sharing scheme for functions. Given a function f, it's splitted or it's shared as f0 and f1, and given any input x in the domain of the function, we independently apply the function f0 and f1, obtain exactly a share of this fx. So this is the function set sharing. Here is a little formal definition. Given a function family, the function set sharing consists of two algorithms. First, the generation algorithm outputs two keys, and next, given the key and the input, and then the two-party obtains the evaluation result of this function set sharing, and the evaluation result is exactly a sharing of this fx. A function sharing satisfies three properties. First, the heading property says actually it's the privacy property. Each key has the function itself. Next, for the correctness means the evaluation algorithm output is exactly a sharing of the original function. And the last one is the compactness or the succinctness, says the key scales with the description size of f. Here we can consider a trivial function set sharing. Like if we directly compute the truth table of this function, and then we can directly share the truth table of this function. So then we will get a function sharing for this function. But the truth table is huge. It's exponential of the input size of this function. So it's not so efficient. So we only consider the function with some succinct description size. In this work, we focus on the two-party case. Here is an incomplete list for the applications of function set sharing, like the private data collection and the writing PIR. Actually, the function set sharing was first proposed to improve the efficiency of reading PIR and also the SQL queries and the oblivious RAMs and also the mixed mode circuit computation. Actually, this is very interesting because we can use some simple function sharing for some simple function classes to implement many complicated functionalities in circuit computation, like the comparison function, the most significant bit function, the shifting operation, multiply, then round, many operations, and also the private heavy hitters, and also the recent construction on private set intersection protocols. Here are some previous constructions of two-party function set sharing. The first one is so first class is the function set sharing from 1V functions. The 1V function-based constructions, we can construct function set sharing for point functions, interval functions, and decision trees. This one is extremely efficient because it's based on 1V function. Next is function sharing for low-degree polynomials from the LPN assumption. Actually, sometimes it's not based on the standard LPN assumption. Some are based on, like this one, based on the sparse LPN assumption. And then the function set sharing for branching programs. Actually, this one is not a direct construction. Given a function set sharing, this construction first transform it to a universal branching program. Briefly speaking, it exchanges the roles of the function at the input, and then using homomorphic set sharing, they encrypt the function, and then the input is public, and they achieve the function set sharing for branching programs from DDH assumption or DCR assumption or LWE assumption or class groups assumption. And the last class is for any polynomial size functions, we can construct function set sharing from multi-key FHE. Actually, this is easy to extend it to multi-party construction. Next, we show our results. First, we give a new notion. It's the PRG with UH. It's a relaxed homomorphic PRG. It's not a homomorphic PRG because ideal homomorphic PRG does not exist. Next, we can instant this new notion from the LWE assumption or the DCR assumption. And then with this EOH PRG, we directly construct function sharing for bit fixing predicates for branching programs. Our construction for branching programs avoiding the universal transformations as in the homomorphic sharing based construction. So our construction is more efficient than previous construction. And also we can construct function sharing for DFA. This is very interesting because for this kind of, the general DFA, the input can be arbitrary. So when we design function sharing, nobody knows the input length. We only use the state transition function of the DFA. Here is a brief efficiency comparison for branching programs. This one, this is for the branching program function sharing construction. from the LW assumption or the DCR assumption. Here, for branching program, L is the length of the branching program, W is the width of the branching program. And then we can see for the runtime, this W square factor is reduced to W over N. And here N is the dimension of the LWE assumption. And for DCR assumption, this W square is reduced to linear on W. And for key size, we can see from LW assumption, this multiplicative factor is reduced to additive factor here. And for DCR assumption, the key size is only reduced from some constant factor. This is 7 to 2. Yeah. And next, we will introduce our techniques. First, we will recall the function state sharing for point functions from previous constructions. First, point function is specified by an input alpha. Here I also given the beta. Actually, beta is not so important. Generally beta can be any non-zero value. If we consider the range is the binary domain or binary range, then the beta is 1. If we can also extend it to a large field or even a large range, but it's not important. We only focus on the alpha because during our design, we only consider this alpha. And this is a point function. And the previous function state sharing relies on the correlated GGM tree. And in the key generation, the two parties shares a correlated GGM tree. This is a path specified by alpha. This is a path specified by alpha. Actually, this is a padding tree of the keys of the two parties. And then during the key generation, they compute the correction word CWI equal to GSI plus the encoding of SI plus 1. This is S1 or this is S1. It depends on the construction. We let this be S1, this as S2, S3 until to Sn. So in the construction, we let this one and this one, this two shares S1. This two shares S2 1. This shares S3 until to Sn1 is this one. So each level, if the two nodes are on the path, then they share the Si1. If they are not in the path, they share this zero or zero vector, like this one, this node. These two nodes exactly share the all zero vector. And how to go from one level to the next level? We use the PRG to achieve this. Okay, this is a brief construction of the previous function for point functions. And next, we consider the bit fixing predicates. For bit fixing predicates, it's a little different. The only difference is here. The input alpha can be a star. Here, star means whatever the input xi is. If it's 0 or 1, both are matched. So we need to extend our construction for this bit fixing predicates. And in this bit fixing predicates, if we consider the same construction, for bit fixing predicates, there are many matched passes like this. Here I only draw 2 because the tree is not so the tree weight is not so large. So here I only draw 2 passes. And if we use the same method, then maybe there are still polynomial matched passes. And then we need to track all of the matched passes as in previous GGM tree-based construction. So the key size becomes still polynomial. So and actually we want to achieve at least a polynomial key size and then with better efficiency. And how do we compress the key size? We use some idea very similar to the previous step. We also sample the S1, S2 until to Sn as in the GGM tree for each level. But here for the bit fixing predicates, we not only let these two nodes share S21, we also let these two nodes also share S21. And then we can imagine for bit fixing predicates, they are super polynomial passes. And then for some level, for some Si1, there are super polynomial passes. So how do we move from one level to the next level? Because in one level, there are super polynomial passes. In next level, maybe there are only one or two sharings of the Si plus one. One idea, a simple idea is to use homomorphic PRG, although it does not exist, and we will explain this later. First, we assume we have an ideal homomorphic PRG like this. Gs plus T is equal to Gs plus GT. And then the correction word is computed as similar to the GGM tree-based construction. We only replace the PRG by the homomorphic PRG. And then during the evaluation, the two parties obtain the share of Si. We assume the two parties are on the path specified by alpha. And then the two party computed as this B times CBI plus, this page a little technical. And then we apply the homomorphic PRG. And after this evaluation, the two party directly obtain a sharing of the encoding of the next level K, Si plus 1. And because this code encoding is some trivial function, so we can directly say the two party actually obtain the sigma 0 and sigma 1 directly share the key of next level with some arrangement of key of next level. And actually, we do not use this one in our construction. So we not use this. We use some tag B. Actually, if the nodes is in the path by alpha, then the T0 T1 share is a share of 1. If it's not in the path, then it's a share of 0. So we move from one level to next level, and with polynomial key sets, because each level we only compute one correction word. So this homomorphic PRG is so useful. It's very useful, but it does not exist. How do we implement this homomorphic PRG? Actually, we define a weaker notion of PRG. This is something like UH PRG, not ideally homomorphic PRG. Given a share of S as S0 and S1, additively shared. And also this GS and the encoding of message is shared as Y0 and Y1. Then there exists a conversion algorithm. It's a local conversion algorithm to convert YB minus GSB equal is exactly a sharing of this M. And this is enough. Actually, we do not need the ideal morphic PRG. This is enough. Why? Actually, this one can be built as the correction word of the last page. This one, the encoding of this S and M. Yeah. So with this, we can directly replace the G by the UHPRG and then this one by the conversion algorithm, and then we obtain the UHPRG. The next question is how to implement this UHPRG. Is this still does this exist? And then we can instant the UHPRG from the LWE assumption or the DCR assumption. Both of the two techniques, like the distributed rounding techniques, distributed discrete logarithm techniques, and also the lifting techniques, both of these two kinds of techniques were developed for the two-party homomorphic sharing scheme for the branching program. So actually the technique are closely related to the previous constructions. And next, we consider the function sharing for branching programs. This is the source node of the branch program, and each level until to the maybe the output for 0 and 1, for 1 or 0. And we can still imagine for a branching program, there are super polynomial evaluation passes. During the design of the function sharing, we don't know the input, so we cannot track or enumerate all of the possible evaluation passes. So we view it as similar to the bit fixing predicates construction. We view each level of the branching program. It has at most W nodes. We will let W is the width of the branching program, and then it has at most W nodes. So we set this level has W vectors. Each is a distinct unit. Each node has a distinct unit vector represent this node, and also with the seed. And then we can use our UHPRG to hide the key of next level, and then use this one to hide this level, hide this level. And then we obtain the function sharing for branching program from UHPRG and the key size only scales with the branching program's key size, the program size. And
Zay, you
with
have about 4.5 minutes remaining.
okay, so here is a summary of the talk. We introduce the EOHPRT abstraction, and then we construct a function structure for bit fixed packets and for branching programs and for DFAs. If you do not have interest to function structure, I mean, I feel this is really interesting. An ideal cryptographic primitive, even if it does not exist, such as an ideal homomorphic PRT, has the potential to significantly simplify the overall construction. That's all for my time. Thank you. Any
Any questions for Zay? Zay, I have a question. Did you guys think about using, for example, key homomorphic PRFs instead of homomorphic PRGs? And is there any advantage in terms of assumptions if you were to build such a construction based on either advantage in terms of assumptions or key size or anything that you might get by assuming key homomorphic PRFs?
Okay, thank you for your question. That's interesting. Yeah, but generally for the key homomorphic PRF functions, I mean it depends on the assumptions. Like for the LW assumption, there are some errors in the final step. The barrier is how to correct the errors to adapt to into our UHPRG framework. I mean, if you want to use in the design for function sharing or something like this, and for the I'm not sure for the DDH based construction, because for DDH based construction, the domain and the range are completely different. I'm not sure we can convert it back from the range of the functions then back to the domain of the function. Yes, that's the answer.
Okay, thank you. If there are no other questions, let's thank Zay and let's thank all the speakers of the session.